Covalent bonding. Okay, so as opposed to ionic bonding, in covalent we're sharing the electrons. It usually occurs between two atoms that if you try to make an ionic bond, it just doesn't work. If you try to transfer or exchange electrons, maybe one becomes more like a noble gas and the other one actually becomes less like a noble gas, and you can't achieve that stability of the noble gas-like configuration through ionic bonds. Almost always between two nonmetals. And so if we look at the periodic table over here, again, if metalloids are this diagonal line going up through here, then all of these guys over here in the top right corner, that's what we're talking about. Bonds between those ones. So between two nonmetals, we get the sharing of electrons. Now, if we could actually see this, what does it actually look like, right, on a molecular level? Well, here's a figure from the textbook that explains it fairly well. As we have our two atoms, right, and they're getting closer and closer and closer together, the first thing to realize that it's these outer electrons that are going to start to interact first. They're the ones that the orbitals are going to start overlapping, invading each other's space, if you will. And more importantly, maybe the electrons from the first one is going to start feeling an attraction to the nucleus of the second one, and vice versa. And so you actually get a stabilizing effect as they start to get close enough to be sensed by the other one. Right? And so if I start way out here on the right side of this diagram where I've got my two atoms and they're so far apart they can't even see each other, there's no interaction happening at all, it makes sense to call that potential energy there zero. No interaction at all, zero kind of energy. But then as I get closer together and I start getting that stabilization effect, then that potential energy drops, becomes more stable, lower energy, that is to say. And it get closer and closer, it drops, but it's going to hit this minimum here at some point. If I get even closer, it actually starts going back up, and so I'm starting to get more unfavorable interactions. And if I try to get really close, it skyrockets way up here into the positive. So why is that? Well, again, I'm getting more stable, but if I start pushing them too close together, then I start crowding those electrons, I start gaining electron repulsions. The nuclei, for that matter, also start repelling because they're both positive, and I'm trying to cram them into each other's spaces, and that's just not going to happen. And so there is an optimal distance right here at the very, very minimum of this potential energy curve, and that would be the distance of, or the size, or the length, if you will, of that covalent bond, where we're sharing those electrons and we've minimized the energy. That is to say, we've made it as stable as it possibly can. Now, covalent bonds are strong, not nearly as strong as those ionic ones are, but still pretty strong. About, I would say, maybe a half to 4 times, that's just a kind of off-the-cuff number, as strong as ionic bonds. So, for example, if I try to take an H2 molecule, hydrogen, which has a covalent bond, and I try to split it up into individual atoms, it's going to take 436 kilojoules. So plenty strong. That's a typical size of the energy to break up a covalent bond. So strong, not as strong as ionic. Now, polar, very important topic here, polar covalent bond. We have electrons, they're being shared. The question is, are they shared equally? Now, there's two ways to think about this. The first way, are they exactly halfway between the two nuclei? So by distance, are they being shared equally? Another way to think about it, are they being shared equally in time? Does half the time the one atom get those electrons and half the time the other one? Or is it more lopsided? 80% of the time one gets the electron and only 20% the other one, right? So either way is an okay interpretation. The question is just, are they being shared equally or not? And it turns out that different atoms do have a different affinity for those electrons. They want them more or less than other atoms. And to try to picture that, if, let's say, an HCl bond, like here in this figure from the textbook, if the chlorine wants those electrons more, it has a greater affinity for those shared electrons than the hydrogen over here, then, well, it's going to hog those electrons. It's going to pull them closer to itself. It's going to hog them. It's going to get them more amount of the time than the hydrogen is. And the net result is it's going to gain a partial negative charge. It's not a full negative, because we're not like an ionic bond where we're giving the electron over totally, but it's hogging it more. It gets 75% of the time, or it's holding it 75% closer, or something like that, right? And so it's a partial negative, and we use little delta, Greek letter delta, lowercase delta there, to signify that. So this partial negative charge would be on the chlorine, leaving the hydrogen with a partial positive. if you have that situation, you actually have a little dipole moment going from the hydrogen to the chlorine. In chemistry, we point towards the negative side, and we have to put a little plus on the positive side just to kind of remind us of that. So this is the partial positive, and it points to where the electrons are being hogged on the chlorine, so that would be the partial negative side. So we get this little dipole. It's a lopsided molecule, essentially. Lopsided, at least the distribution of the electrons being shared. That's an important thing. Electronegativity, which is going to quantify this, we're going to get to it in just a second here, is a measure of those shared electrons. If you're not sharing the electrons, then this whole discussion is meaningless. It's got to be the shared electrons in a covalent bond. Alright, so we would say that that's a polar molecule. It's a polar bond. It's just this idea of unequal sharing. Alright, so electronegativity as devised by Linus Pauling. There's other formulations with slightly different values for electronegativity, but I think Linus Pauling is still the most often used. Defined as the tendency of an atom to attract those electrons toward itself. And again, I would add that very important caveat within a covalent bond. The shared electrons are what we're talking about. And if you rank these then, this was fairly arbitrary. Pauling decided to rank it between 0 and 4. And so 0 would be just no tendency really to pull it to itself at all, very, very little, to 4 being the highest tendency to pull those electrons and hog them, share them, not share equally. Right? And if you look at this, the very, very lowest one down here, francium, cesium actually is tied, 0.7, so that's low on his scale, not very electronegative. These guys really don't have much tendency to pull those electrons towards themselves. Well, that kind of makes sense. We know the ones over here on the right side of the table like to be positive, so why would they want to pull electrons toward themselves and make themselves more negative? That doesn't make any sense, right? And so it makes these low values make a lot of sense on that simple basis alone. Where's the very highest one? Fluorine. Up here, 4.0. 4.0, that's the highest, absolute highest you can get on the electronegativity. The closest one to it is oxygen, which is 3.5, right? And after that, nitrogen and chlorine are tied at 3.0. I mean, but fluorine is a full one whole unit, one whole step above them, and so fluorine is really highly electronegative, more electronegative than anything else, any other element out there. It's the top. And if you look at these general trends, I've drawn it in with this yellow arrow. It kind of goes from the low side here on the bottom left of the table to the high side fluorine here on the top right. And so if you're trying to compare any two atoms, you're trying to look to see, hey, the more electronegative one is going to be more up and more right on the periodic table, always. If you look at the most electronegative ones, again, fluorine, top, king, oxygen, nitrogen and chlorine are next equal, bromine, and then these three, iodine, sulfur, carbon, are next, all equal to each other, and then finally here, hydrogen, phosphorus. And there's a, not that you probably need to, but there's a way to, you can remember that order. Flame and oxygen, nice, clear, bright. I suspect canned, hydrogen, period. If you ever have to remember the order of the most electronegative atoms, which actually becomes important in organic chemistry if you go on to that. But anyway, there you go. Flame and oxygen, nice, clear, bright. I suspect canned hydrogen, period. That'll get it to you, and you just got to remember that these two are all equal and these two are equal, and otherwise it gives you the order of those electronegativities. Don't need to worry about that now, but just for the future. Alright, so I have a way to quantify how much an atom wants to pull those electrons toward itself. And the idea is, well, if I take two atoms that have the same electronegativity, they both have the same pole, and so those electrons will be shared perfectly evenly. But if I've got one that's stronger than the other, then they're not going to be shared equally. Right? And so the question is, well, how different in electronegativity does it have to be before I can start to see and get some influence, or some effect, I should say, of this unequal sharing? So how large of a difference? And that's the key, looking at the change, delta, the change in electronegativity. That will tell me, first of all, if it's polar or not, and if it is polar, just how polar it is. The larger the delta En, the more polar that bond will be. If you think about this, if I've got 0 difference, zero difference, then they're going to call that a pure covalent, pure in the sense that perfectly even sharing. Not lopsided at all, not polar, just pure covalent. Okay. And then, as I get to larger and larger electronegativity, let's go to the other extreme. Let's say it's just huge. Let's say it's to the point where my one atom gets it 95% of the time and this one only 5%. Or let's even push it forward. 99% of the time this one gets it and only 1% of the time this gets it. Well, at some point, I have to say, it might as well be like an ionic bond. I mean, if this one's going to get it 99% of the time and this one only 1% of the time, it's as though the electron was transferred from this atom to that one. Right? So if it's that lopsided, that large of a difference in electronegativity, well, that's what we'd call ionic. We're truly giving it over. Okay? And that's what this is showing here. Large, it means ionic. But if it's somewhere in the middle there, well, we're going to say, hey, they're still sharing those electrons, but it's polar. It's not this pure idea of equal sharing, but it is polar. And the larger the delta En, the more of this polar and finally ionic character that bond actually has. So where are our dividing lines? I've seen different textbooks use different values. This one sets it up like this. And so I green box it. This is important. If it's less than 0.4 difference, so if you subtract those En numbers for the two atoms involved in the bond and it's less than 0.4, we're going to call that pure covalent. All right. It might be ever so slightly lopsided, one's ever so slightly more electronegative, not enough to worry about, not enough where we really start seeing any effects due to it, and so we're going to call those pure covalent. If it's between 0.4 and 1.8, those are polar covalent. So here it's lopsided enough where I'm starting to get some effects from it, right? But it's still sharing. And then finally, if it's greater than 1.8 here, well, we'll call that ionic. That's where it's, it's hogged so much by one of the atoms that, shoot, we're just going to call the thing ionic. Okay. So you can say, hey, ionic, or from the left and the right side, and that's almost always true. But you might get some pairs of atoms that are bonded that it's kind of hard to tell. I don't know. Is that left-right rule good enough? Or the real way is to look at the electronegativity. See what the difference is. Right? Subtract the one from the other. If it's greater than 0.4, it's going to be a polar covalent. If it's greater than 1.8, hey, it's so darn polar, we're going to call it ionic.